We're looking at 7.1 quiz morning review. Let's look at number one here. Uh, Write the integral that would give the area of the shaded region to the right, but we're going to set up but not solve. So we have this quadratic curve function here, y equals 4 minus x squared. And notice that this graph crosses the x-axis at a certain x value, and that causes there to be a flip in the top and bottom curve. So we have two shaded regions. We want to find the area, the total area of both, or create a definite integral setup that will produce the area of those two shaded regions. But we're going to have to rely on more than just one definite integral, because this shaded region does not have the same top curve and bottom curve as the second shaded region. Notice that the left shaded region has the top curve of the 4 minus x squared, but after this intersection, the top graph is actually now going to be the x-axis, and the bottom curve becomes the quadratic 4 minus x squared. So we're going to have to rely on two separate definite integrals to find the areas of the two regions. So first thing we need to do is to identify where the intersection is. So to find the intersection, we can set the curve 4 minus x squared equal to the x-axis equal to 0, and then we can solve for x. So if we set 4 minus x squared equal to 0, we solve for x, we get plus or minus 2. Notice that negative 2 is not in the interval. We only care about the interval from x equals 0 to x equals 3. So negative 2 is not in that interval. In fact, it's actually going to be this. If we follow this parabola past the y-axis, it's actually going to end up over here at negative 2. So we expect, it makes sense that negative 2 does, the graph does cross the x-axis at negative 2, since we have a parabola that opens down. So, but we know that x equals 2 is going to be the interval that, the bound that we are concerned with. So the first definite integral will be from 0 to 2 of the top curve minus bottom curve. Top curve is 4 minus x squared. Bottom curve is the x-axis, so 0. So top graph minus the bottom graph from 0 to 2. And then the second region will be a top curve of 0 and the bottom curve of 4 minus x squared. So top graph minus the bottom graph. And then the bounds are going to be from 2 to 3. And then once we have that, we can clean that up a little bit, and then we're not asked to solve. We just have to set up the definite integrals that represents the eventual area. All right, number 2, find the area bounded by the following regions. We have y equals x squared. That's the parabola here. We have x plus y equals 6. And if we write it in slope-intercept form, we can write it as y is equal to negative x plus 6. So negative x plus 6 is a linear graph that has y-intercept of 6, and the slope of negative 1. So we see that based off of this graph, the parabola, the linear graph is going to sit above the curve in the shaded region. So then we just have to find the intersection so that we can know where the bounds are going to be. So we set x squared equal to 6 minus x. When we do that, we solve. We can bring everything over to one side, say equal to 0, and then go through factoring. So go through factoring, we get x plus 3, x minus 2, so x equals negative 3 and 2. So from negative 3 to 2, notice that we have to do top curve minus bottom curve, or top graph minus bottom graph. Top graph is a linear function, 6 minus x. The bottom graph is the x squared. So top 6 minus x minus the bottom x squared from negative 3 to 2. And we can go through Powell rule. Once we go through Powell rule, we found the antiderivative. So then we can plug in the upper and lower bounds. So plug the upper bound into the remaining antiderivative, minus, and then plug in the lower bound into each of the x of the antiderivative, and then we clean this up, and we get 125 over 6. Okay, number 3. We have x minus y squared equals 0 and x minus y equals 2. If notice that this is x equals y squared, so this equation is not quite a function, but when y is positive, when y squared, we know that this is going to be a parabola that opens to the left or to the right, and this is a positive y squared, so it's going to open to the right, and the parabola is going to be through the origin. X equals y plus 2, that's the same thing as y is equal to x minus 2, so that's simply a linear graph that goes through, that has a slope of 1 and y-intercept of -2, so a graph that looks like this. So we need to find the intersection. Intersection between the two graphs will be in terms of y, because we want, notice that the way that these two graphs are related to one another in the shaded region, as boundaries of the shaded region, is going to be a right graph minus the left graph. So we want to be able to set up using our doing right minus left, meaning that we have to find our boundaries in terms of y. So we can set the parabola y squared equal to the linear graph y plus 2. We set them equal to each other to find the intersections. We have to go through factoring, so we bring everything over to one side, say go to 0. Y minus 2 times y plus 1. We solve for y, we get y equals 2 and y equals -1. So our lower bound is -1, our upper bound is 2. Our right graph is going to be y plus 2. Our left graph is going to be y squared. So y plus 2 minus y squared. We go through our antiderivative steps, going through power rule. Y becomes y squared over 2. 2 becomes 2y. Negative y squared becomes -y cubed over 3. Plug in upper and lower bound. And then we have our area of the shaded region. All right, let's look at number 4. We have y equals x cubed plus x squared. We have basically a cubic function here. So we have a cubic function here. And then y equals 6x, so we have y equals 6x here. It may not be apparent as to how this graph is going to look. However, we can start by finding intersections. So the way we find intersection, we can set these two equations equal to each other. We get x cubed plus x squared is equal to x6x. Bring everything over to one side, go through factoring, take out the GCF of x, factor the rest, x plus 3, x minus 2, so x equals 0, -3 and 2. So we may, since we have 3 boundaries, there is a potential that we may have two separate, we may have a change in the top and bottom curve, similar to what we saw with this first example here. Okay. So it may be tough to know exactly which one is the top graph and which is the bottom graph, but we can just go ahead and set this up, right? We can set up, well, we know that for sure we can say -3 to 0 of top minus bottom, and then from 0 to 2 from top minus bottom. There may or may not be a change in between these two functions. They may not overlap. But what we can do is, if we want to determine which of these is the top function, which one is the bottom function, without being able to graph, what we can do is we can choose a x value that sits between -3 and 0. In this case, let's say -1. And we can plug -1 into both functions and see which one produces the larger value. Okay? Whichever produces the larger value must be the top function. Whichever is the lower value must be the bottom function. So if I plug -1 in, I get -1 plus 1, which is 0. If I plug -1 in for x, -1 times 6 is going to be -6. So 0 is a larger y value than -6. And then so because of that, we know x cubed plus x squared will be the top curve and 6x is the bottom curve. For the second region, from 0 to 2, we can choose a value between these two boundaries. Let's say x equals 1. So we can plug 1 into 6x, which is, 1 is 6x, we get 6. 1 for x cubed plus x squared, so 1 plus 1 is 2. 6 is greater than 2, so we know 6 is going to be the top graph. It's going to be physically higher up on the graph than the x squared plus x squared, x cubed plus x squared in this interval. So that's how we know 6x is the top graph, x cubed plus x squared is the bottom graph. So once we set this up, then we can just go through our antiderivative steps, power rule. Once we apply power rule, we can plug in upper bound, then subtract the lower bound. Go through power rule, then we can plug in upper and lower bound, and then it's just a matter of going through all these steps of adding fractions, combining these terms. In the end, we get 253 over. All right, last one here, number 5. Find the area of the shaded region. We have y equals square root of 4 minus x. That's this curve that's over here. We also have y is equal to positive square root of x plus 4. We can do this as top minus bottom. Okay, so if we want to do top minus bottom, we have to notice a couple of things here. One is that notice this top graph, top curve of the shaded region is not consistently the same curve, same graph. From -4 up until the y-axis is going to be this positive square root of x plus 4, and but then immediately to the right of the y-axis, the top curve suddenly changes to square root of 4 minus x. So that's one thing to notice. Another thing is to notice is that we're going to have to need 2 separate integrals, and we're going to have a switch in the top curve at x equals 0. So we can set up using our 2 separate integrals. One is from -4 to 0, top curve, square root of x plus 4 minus the bottom curve, which is going to be the x-axis, which is 0. So top curve minus bottom curve. And then the second integral, top curve is the square root of 4 minus x. Bottom curve is a 0, so square root of 4 minus x minus 0 from 0 to 4. And then we can go through u substitution to set up both of these. So u substitution, we let the u value be x plus 4, which then allows du to be dx. Go through power rule, u to the 1/2 becomes u to the 3/2 over 3/2. Plug in upper bound and lower bound, we get 16 over 3 minus 0. And if we do this same thing here, square root of 4 minus x, we're going to get negative 16 over thirds. So we get 16 over 3 minus negative 16 over 3, and we get 32 over 3. Another way that we can go about doing this, we can do right minus left. If we do right minus left, all we need is one definite integral, because notice that the right, this curve is always to the right of this curve here. Okay, no matter where we draw horizontal lines between these two curves, the right endpoint of each horizontal line will always hit the same curve, and the left endpoint of every horizontal line we draw will also will be consistently hitting the other curve. But if we do right minus left, we have to adjust our bounds, which will suddenly become, instead of from -4 to 4, it'll be from the lowest y value, which is 0, to the highest y value of the shaded region, which is 4. Right? Sorry, 2. That's the highest y value there. And also we have to adjust the equation. No longer in terms of x, has to be in terms of y, so we have to solve for x. X is y squared minus 4, and here x is equal to 4 minus y squared. So the right curve is going to be 4 minus y squared. That's the right curve. Left curve minus the left curve is y squared minus 4. We do right minus left from our lower to upper bound, and we can combine like terms first. Once we combine like terms, then we can go through power rule. Once you go through power rule, plug in upper and lower bound, we should get the same result, and we do 32 over 3.